In this lesson, we're going to focus on solving problems associated with polyprotic acids. So sulfuric acid is a polyprotic acid. Notice that it has two hydrogens per formula unit, so it's a diprotic acid. Now, how can we calculate the pH of H2SO4 if the concentration of it is relatively large? Now, you need to understand that there's two dissociation reactions that you need to deal with. The first hydrogen comes off easily. The first Ka value, which represents the acid dissociation constant for the removal of the first proton, it's very large. And so it ionizes almost 100%. So we started with a concentration of 3 moles per liter. So then this is going to become 3M, and the same is true for the bisulfate ion. Now the second proton doesn't come off so easily. And so this reaction is in equilibrium. And the Ka value for the second step is this number. It's 0.012. Now here's a question for you. The amount of H plus that we get in a solution from the second step, is it significant? It turns out that when the concentration is high, it won't be significant. So the pH of the solution is simply going to be negative log of the hydronium ion concentration, which is 3 moles per liter. And so you can get an estimate, which is going to be negative 0.477. So that's an estimation of the pH of the solution. Now, if you want to find the exact answer, it's going to be slightly different, but we need to take into account the amount of H plus that's released from the bisulfate ion. So let's make an ice table. So we have the initial concentration of the bisulfate ion, that's 3 moles per liter. And the same is true for H plus. Now sulfate is 0, so the reaction has no choice but to shift to the right. So this is going to increase by X, and the reactant is going to decrease by X. So that's going to be 3 minus X, 3 plus X, and X. So now we can write the Ka2 expression. So it's going to be the ratio of the products, which is going to be these two, H plus times the sulfate ion concentration, divided by the reactant, HSO4 minus. So Ka2, that's 0.012, and that's going to be 3 plus X times X over 3 minus X. Now, if X is small, 3 plus X is going to be approximately 3. So we could cancel 3 plus X and 3 minus X, because 3 minus X will also be about 3. So therefore, we could see that X is equal to this number, 0.012. And keep in mind, that is simply an approximation. But now, to check to see if our approximation makes sense, we can plug it back in. So let's plug it into this expression, and let's see if we get a number that's close to 0.012. So it's going to be 3 plus 0.012, that's 3 plus X, times X, divided by 3 minus X, or 3 minus 0.012. So go ahead and type this in. So this is equal to 0.0121, which is very close to this number. So the approximation is acceptable. Now that we have the value of X, we can now calculate the H2O plus concentration. So based on the ice table, it was 3 plus X, so that's 3 plus 0.012. So the contribution of H plus from the second step is very small. However, it will change our answer slightly. So now we can calculate the pH of the solution. So it's going to be negative log of 3.012. And so that's going to be negative 0.479. So these answers are different if you round it to the thousandths place. But if you round it to the hundredths place, it's going to be about the same, which is approximately negative 0.48. Now let's try this example. Calculate the pH of a 0.02 molar H2SO4 solution. So this time, the concentration of H2SO4 is low. So let's see how this problem is going to be different from the last one. So the first thing we need to realize, just like before, is the first proton is going to come off easily. So we're going to have 100% ionization. So this is going to be 0.02, and this is going to be 0.02 for the first step. And now let's move on to the second step. So we're going to make an ice table for it. Now the second step is a reversible reaction. So we need to write 2 arrows as opposed to 1. And now let's make the ice table. So the concentration of bisulfate is 0.02 initially, and the same is true for H+. Now because this is 0, the reaction has to shift to the right to increase the amount of sulfate that's in the solution. So this is going to be plus X and minus X on the left side. So now Ka2 is going to be the ratio of the products divided by the reactants. And Ka2 is 0.012, and H+, I forgot to put 0.02 plus X. Very important. And sulfate is simply X. And then bisulfate, 0.02 minus X. Now this time, we can't just say that X is 0.012, because 0.02 and 0.012 are very close. So X cannot be ignored. It's important this time. So what we need to do is we need to use a quadratic equation. But first, we need to rearrange what we have. So let me get rid of this. And just keep in mind that H plus is 0.02 plus X. We'll need that when we need to calculate the pH later. Now let's cross multiply. So 1 times all of this stuff is just going to be 0.02 plus X times X. And if we distribute the X, it's going to be 0.02X plus X squared. And then 0.012 times those two. If you multiply 0.012 by 0.02, that's 0.00024. And then minus 0.012x. Now we need to put it in standard form for a quadratic equation. So we want to write it like this. On the left, I already have x squared. Now I need to take this term, move it to this side, where it's going to become positive on the left side. So it's going to be 0.02x plus 0.012x on the left side. And so that's going to be 0.032x. And I'm going to move this to the other side, where it's going to switch from positive to negative. So now let's use the quadratic formula. So it's x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So b is the number in front of x, which is positive 0.032. And then we're going to have b squared minus 4. A is the number in front of x squared, so that's a 1. And c is that value, negative 0.00024. All divided by 2a. Now, if you type in 0.032 squared minus 4 times negative 0.00024, you're going to get 0.001 0.1984, and then take the square root of that number. So that's going to be 0.044542. Now, if we use the negative sign, x is going to become negative, which won't make sense. So we're going to have to use the positive sign. So it's going to be negative 0.032 plus 0.044542, and then take that result divided by 2. So x is 0.006271. Now let's check it. We said that Ka2 was going to be 0.02 plus x, that's the H plus concentration, times the sulfate concentration, divided by the bisulfate concentration, which was 0.02 minus x. So let's plug in x into this expression, and let's see if we get a number that's very close to 0.012. So go ahead and type this in, 0.02 plus 0.006271, and then times this number, and then divided by 0.02 minus 0.006271. It's always good to make sure if your answer is correct. So I got 0.0119998, which we could round it and say that's 0.01. And because we have a 9 here, this can go up to a 2. So it rounds to 0.012, which means that we have the right x value. So now we can calculate the H2O plus concentration. So it's 0.02 plus 0.006271. So the contribution from the second equation from bisulfate is significant to the H2O plus concentration. So it's 0.026271. So the pH, which is going to be negative log of this number, is 1.58. So that's the pH of the solution. Now let's say if we made an estimate, if we simply use that number. If we use negative log 0.02, then the pH that we would have gotten would have been 1.70, which is significantly different from this answer. So this is the more accurate answer. So that's the pH of the solution, is 1.58. Number 3, calculate the pH of a 2 molar H2PO4 solution. And in addition, we need to calculate the equilibrium concentrations of phosphoric acid, H2PO4-, hydrogen phosphate, and phosphate as well. So let's start with the first one. So phosphoric acid is in equilibrium with H plus and H2PO4-. And so we need an ice table. The initial amount of H2PO4 that we have is 2. This is 0, and so the reaction has to shift to the right. So this is going to be 2 minus x, and that's going to be x. So Ka1 is going to be the products, H plus times H2PO4-, divided by the reactant, H3PO4. So Ka1, that's 0.0075. And that's going to be equal to H plus, which is x, H2PO4 is x, and H3PO4, it's 2 minus x. Now the question is x small or is it significant? Well, let's assume that it's negligible. So we're going to get rid of this value first. So what we're going to have to do is cross multiply. It's going to be 0.0075 times 2. which is 0.015, and that's equal to x times x, or x squared. Now, if we take the square root of both sides, x is going to be 0.1225. So that might be slightly significant. Let's plug it back in to see if we'll get a significant answer. So 0.1225 squared divided by 2 minus 0.1225. That's going to be 0.008. It changes a little, but not by that much. So what I'm going to do is use the quadratic formula, because I think x is significant in this example. So let's get rid of that, and let's cross multiply. So here we're going to have x squared, and that's going to equal 0.0075 times 2, which is 0.015, and then times negative x, so that's going to be negative 0.0075x. So let's move everything to the left side. So it's going to be x squared plus 0.0075x, and then minus, this is not supposed to have x. I don't know why that's there. So x is going to be negative b, so b is the number in front of x, plus or minus the square root of b squared minus 4 times a, which is 1, and c is negative 0.015, which is that number, divided by 2a, or 2 times 1. So this is going to be negative 0.0075, and then 0.0075 squared minus 4 times negative 0.015. That's about 0.06. And if we take the square root of that number, it's going to be plus or minus 0.245064 divided by 2. Now I'm going to use the positive sign because I don't want a negative x value. So negative 0.0075 plus 0.245064 divided by 2 will give us an x value of 0.1188. The other x value that we had was 0.1225, so a small difference, but still significant. So now we can calculate the concentration of H2PO4. So that was 2 minus x in the ice table. So that's 2 minus 0.1188. So at equilibrium, the concentration is going to be 1.881. So that's the concentration of phosphoric acid. Now the concentration of H2PO4 minus, based on the ice table, it was equal to x. So that's 0.1188. Now this is also equal to the H3O plus concentration. So we could therefore calculate the pH of the solution. So it's going to be negative log of 0.1188. So the pH of the solution is 0.925. Now let's calculate the concentration of hydrogen phosphate. So let's write this reaction. H2PO4 minus is in equilibrium with H plus and HPO4 2 minus. So we can use the expression for Ka2. It's going to be H plus times HPO4 2 minus divided by H2PO4 minus. Now we have the value of Ka2. It's 6.2 times 10 to the minus 8. And the concentration of H plus is this number, So that's 0.1188. And our goal is to calculate the concentration of HPO4 2 minus. And H2PO4 minus, which is here, it's also equal to X. So that's 0.1188. Now, because these two numbers are the same, it turns out that the concentration of HPO4 2 minus is equal to Ka2. So I'm going to write that here somewhere. So HPO4 2 minus is equal to 6.2 times 10 to the minus 8 moles per liter. So now, we only need to calculate the concentration of phosphate at this point. So HPO4 2 minus is in equilibrium with H plus and the phosphate ion. So we can write the expression for Ka3. So it's H plus times phosphate divided by hydrogen phosphate. So Ka3 is 4.8 times 10 to the minus 13. And H plus is the value of X, which is 0.1188. Now our goal is to calculate the phosphate concentration, and we now have HPO4 2 minus, which is this number. So it's going to be 4.8 times 10 to the negative 13 multiplied by 6.2 times 10 to the negative 8, and then divided by 0.1188. So the phosphate concentration in this example is 2.51 times 10 to the negative 19. And so that's it for this problem. So here's the last problem. So we have a solution that has these four species: phosphoric acid, hydrogen phosphate, dihydrogen phosphate, and phosphate as well. So which is the predominant species at a pH of 1.5? Now we're given the Ka values. So what we need to do is calculate the pKa values. So let's start with pKa1. It's going to be negative log of Ka1. So negative log of 7.5 times 10 to the minus 3, that's 2.12. And then pKa2, that's going to be negative log of 6.2 times 10 to the minus 8, and so that's 7.21. And finally pKa3, that's a negative log of 4.8 times 10 to the negative 13, and so that works out to be 12.32. Now what we're going to do is make a number line, and you want to place the pKa values in this number line. So this is going to be 2.12, 7.21, and 12.32. Now what you need to realize is that at a pH below the first pKa value, the predominant species is going to be phosphoric acid, and then take off a hydrogen is going to be H2PO4 minus, and then HPO4 2 minus, and then phosphate PO4 3 minus. So considering part A, at a pH of 1.5, which is here, the predominant species is going to be phosphoric acid. In part B, at a pH of 5.2, it's going to be dihydrogen phosphate. And then in part C, at a pH of 9.4, it's monohydrogen phosphate. And then in part D, at a pH of 13.8, it's going to be phosphate, which is somewhere in that region. And so, as the pH increases, you need to take off a hydrogen atom. The number of hydrogens that's going to be on the phosphate ion will decrease. So that's how you can determine the predominant species in a solution if you're given the pKa values and if you know the pH of the solution. Now let's move on to part E. What is the pH of a 0.5 molar H2PO4 solution? Now H2PO4 is right here. So we know that the pH has to be between 7.2, actually that's not H2PO4, I take that back. This is H2PO4 minus. So the pH has to be somewhere between 2.12 and 7.21. So if we have a solution that's almost 100% H2PO4 minus, you can estimate the pH with this equation. It's going to be 1/2 the sum of these two pKa values. So basically, it's the average of pKa1 and pKa2. So it's 1/2 pKa1 plus pKa2. So that's going to be 1/2 of 2.12 plus 7.21. So 2.12 plus 7.21, that's 9.33. And then if you divide that by 2, we can get an average pK value of 4.67. So the pH of the solution, if we only have dihydrogen phosphate, is going to be 4.67. Now let's move on to part F. What is the pH of a solution consisting of 0.5 hydrogen phosphate and 0.5 m phosphate? So here we have a buffer. We have equal amounts of the weak acid and the weak base. And whenever you have equal amounts of acid and base in a buffer solution, the pH is equal to the pKa. So here is the acid, HPO4 and here's the base. And here's the pKa that's between them. So the pH is going to be equal to the pKa, so it's 12.32. So let's review what we just learned briefly. So let's say if we want to calculate the pH of a solution that's almost 100% HPO4 So if you just have one of these, to estimate the pH is simply the average of the two pKa values. So we're focused on this one. So we just got to average 7.21 and 12.32. So it's 7.21 plus 12.32. And then after you add them up, divide by 2. So the pH there is going to be about 9.8. So if you have 100% of one of the intermediates, just remember the pH is simply the average of the two pKa values that surrounds that intermediate. Now, let's say if we have a buffer solution, 50% is H3PO4 and the other 50% is, let's say, H2PO4 minus. So that's between these two. If we have a 50-50 mixture, the pH is simply equal to the pKa. So in this case, it's going to be 2.12. Now let's say if we have a 50% mixture of H2PO4 minus and 50% of HPO4 minus, so that's these two, the pH is going to equal to this pKa, which is between those two species, so it's going to be 7.21.